What's up, you guys? This is my second time saying what's up because I had my first recording done, but I kind of went off on a tangent about Asian food, and that took a good minute and a half, and I thought, well, that wasn't relevant, so I pressed stop and I deleted the video because I don't think this software can allow you to like cut different parts of the video and put them together, you know. Although if I made two videos, I think editing would have taken a lot less time than remaking this video. But you know, like when you're writing an essay and you just type like an entire sentence, like if I type in like I'm typing in one hand, Mr. Kim is the best, and you're like, oh, I misspelled the, so you like, or I didn't put a period right here, so you like backspace everything. Mr. Kim is, and you're like, oh, I capitalized Mr. So you know what I mean, right? So I probably could have edited the videos. I've already spoken for a minute 30 seconds. So this is already off on a tangent, but I'm not re-recording. All right, you guys, let's do matters or states of matter. So I decided that I'm not gonna go into the details or until we come back. So we'll do that on Friday. So just very basics of states of matter, just to kind of save half a day. So you guys probably all know that we have three states of matter. We're not going to talk about plasma in this class, so but there is, technically a fourth state of matter, but we're not going to talk about plasma because plasma has properties that aren't very consistent. Anyways, we have solids, liquids, and gases. I used these pictures last year, but you guys all know what solids are. Anything that's pretty much rigid. We have liquids, right? Anything that's liquidy, and then gases, right? This picture explains it well. Now, some basics. Okay, solids have definite shape and volume. This means that the atoms are very closely packed. Okay, they're very closely packed, and although the atoms do vibrate, they are, of course, we don't see it happen. They're too small on an atomic scale, but then they're so closely packed that to the naked eye, it's solid. It's solid. The shape does not depend on the shape of the container. This just means that if you were to have this wooden table, right? This shape of the wooden table doesn't the container that's holding this wooden table, although we probably wouldn't have a wooden table container, that container doesn't determine the shape of this table. This table is always going to have four legs no matter what. If we put in a big box, the box shape is a cube, but that cube is not going to determine the shape of this table. Make sense? Liquids have indefinite shape and a definite volume. What is it? What this means is that depending on which container you have, in this case we have a cylindrical glass over here. Can you guys see my mouse? I hope you guys can. We have the cylindrical cup, so glass. So the liquid inside it is going to the atoms are going to move, right? Kind of slide along until it fills this volume. Or it fills this shape. Okay, so it has an indefinite shape but a definite volume. Of course, we can't just bring more liquid out of nowhere, right? We have a certain amount of liquid that's going to fill this shape. Okay, the shape does depend on the shape of the container. Okay, and again, the atoms are flowing now; they're less bonded together per se. Okay. The gases, indefinite shape and a definite volume. Same idea as liquids. Actually, very similar behaviors, except that gases, right? Since they're really loosely held with one another, the atoms, they're moving all over the place. They have a lot of energy. Okay, the shape does depend on the shape of the container, just like liquids do. Okay, that's some basics. We'll cover this other stuff on Friday. So I wonder if this works. I didn't actually test this out yet, but hopefully you guys are seeing PowerPoint mode right now. So change to the state. We're going to be talking a lot about about kinetic energy in this class, particularly when we go to our thermochemistry unit. But anyways, if you look at this diagram, it's very self-explanatory, but um, let's delve into it deeper. Okay, so as you see over here, I'm looking at, I don't know if you can see my mouse right now, but I'm looking at the left where it says gas condensation. It's like the particles are all floating around, as you can see, right? They're moving around really fast. So we have our gases, and the middle circle over here, we have liquids where they're still moving around, they're floating, they're flowing, but they're still more compact than gases. And then we have solids where we have this circle over here with atoms inside it that's just very rigid and they're really tightly bonded and they're just sort of vibrating, or they are vibrating, but they're not flowing. Okay. Um, so as we increase or as we move towards the left of this diagram, what increases? I'll give you guys about 4 seconds. And kinetic energy, right? I said this at the beginning. So as we um, put in more energy, and we'll talk about what that is again in thermochemistry, exactly what energy is. As we put in more energy, this quantifiable amount, um, our atoms are going to have more kinetic energy, hence they're going to be moving around more. Okay. Kinetic energy is energy of motion, by the way. Um, Evaporation, melting, freezing, condensation, we're going to get to on the next slide, so I'm going to skip that for now. Okay, so maybe you guys seen this before, maybe not. This is what you call a phase diagram. You might see this in your SATs, like for a math problem. Like they'll use this diagram in some way to test your math skills. I'm not sure, but anyways, this is a very popular graph, and this basically shows you the relationship between pressure and temperature amongst the 3 states of matter. Okay, so as you can see, just based on this graph, you guys learn how to graph in algebra or in biology and algebra. As we increase the temperature, you can see that we're mostly in that gas stage, correct? And I'm not talking. I don't care about pressure right now. I'm just saying, relatively over here, I'm looking at the right side of the chart. If my mouse isn't here, the right side generally, most of it is gases because we're increasing the temperature, right? Because higher temperature will mean the atoms are hotter, right? We're never going to say that again, but warmer, so more kinetic energy, so it's going to move around more, so it's going to want to be a gas. Also, if the pressure is really low, we're going to talk about exactly what pressure is and how it affects energy when we go talk about gas laws in our gas units. But as pressure decreases, right, we're most likely going to stay with our gases. And so you can, ideally you can predict, depending on which mixture, which substance we're talking about, like how much temperature and how much pressure we would need for that mixture to be in the solid state, the liquid state, or the gas state. Okay, and of course the numbers and the numerical values will be different for each of these variables. Okay, just a couple of things I want you to take a look at. Where the what do you call these? The dots, the points, the 2 points that you see over here, triple point and critical point, these will be very important. You are required to know what these are. But before we do that, all the different phase changes like melting, freezing, vaporization, condensation, sublimation, and deposition, you've seen those terms before. So I'm not going to explain exactly what they are, right? But know that that particular term um, defines how one state of matter is changing to a different state of matter. Okay, so you guys all know that going from solid to liquid is called melting, and the liquid to solid is freezing, right? Same thing with some of you guys may not have heard of sublimation. The sublimation is going from solid to gas, and deposition is going from a gas to solid state. Okay, so we're just only changing states. That's how we describe. That's the terminology, the diction we're going to use for chemistry. Now, triple point and critical point, let's take a look at that. If you take a look at triple point, it is pretty intuitive, right, what that point is for, especially since the actual word is, the word has the word triple in it. So Triple point is, give you guys just 2 seconds. Triple point is when, of course, where all three lines intersect, but that's when you have a mixture or a substance that exists as solids, liquids, and gases at the same time. Okay, um, most chemicals are are scientists have a difficult time achieving the triple point for most chemicals, but water is, and I say this loosely, is pretty easily doable, right? If you guys see, I don't know why I don't have a picture here. I'll show you on Friday. But if you have a triple point of water, you'll see like the top layer is gas, and the middle layer is liquid, and the bottom layer you see ice, or right, so frozen water. So it's pretty cool. Okay, and you guys know this term equilibrium. My voice is cracking. Equilibrium. Um, where was I? Critical points. The critical point is not so obvious. So let me state out the formal definition, and I'll kind of go back to the picture and explain. It's when the liquid vapor line ends, the critical temperature and pressure of the substance. Oh, multiple definitions. Beyond this, uh, it cannot condense from gas to liquid because the particles have too much energy. Sorry guys, I'm tired. So what this means is, and you can go back to this definition later, I stuttered a couple times. What this means is after this point in time, okay, um, it's the point where no matter how much we increase the pressure or the temperature, right, we're gonna have this super critical stage. Okay, so if I draw a line like that, again, if you don't see my mouse, I'm just drawing a horizontal line from the critical point. And if I draw a straight vertical line from the critical point, that region, okay, that region of this chart, okay, is a region where we don't have gases or liquids, but it's at a super critical state. Okay, so that's kind of hard to visualize. And it really is. Um, and once you reach that supercritical stage or state of matter, it will probably look like a gas. Okay, I will show you a picture on Friday. It does look like a gas, but it's not. It's at a supercritical point where, at this point, no matter how much you increase the temperature or how much you increase the pressure, that does not matter. We have reached this state, um, this supercritical state. Okay, so although there is a little bit of green past the critical point and a little bit of purple past the critical point, just remember that there is this axis over here, okay, that defines the supercritical state. And you can also tell because the dark line that kind of lines the phase transitions ends at the critical points. Above the critical point, there is no dark line, so we're not going from gas to liquid. Okay, we're not transitioning anymore past that critical point. All right. Well, that's a basic rundown of states of matter, and the rest of the stuff we will explore on Friday. And again, we're gonna delve deeper uh, on Friday on changes of state. Okay. And that was almost 14 minutes. I apologize for the long video, and I will be quiet right now. Peace.